Look up at the night sky. You see stars, you see galaxies, you see a vast, silent, cosmic ocean. It seems chaotic, but it is not. Everything out there, from the smallest atom to the largest supercluster of galaxies, follows a set of rules. These are the laws of physics. They are elegant, they are powerful, and they are built upon a handful of very special numbers: C, G, H. These numbers are the bedrock of our reality. They dictate how stars burn, how planets orbit, and how life itself can exist. We have measured these numbers with incredible precision. But what if we are wrong? What if, after all our work, we find a small hidden error in one of these fundamental values? What happens then? So, what are these fundamental constants? Think of them as the universe's own secret recipe book. If you want to bake a cake, you need a recipe. It tells you exactly how much flour to use. It tells you exactly how much sugar to use. It tells you exactly how much butter to use. Get the amounts wrong, and you do not get a cake. You get a mess. The universe works the same way. The fundamental constants are the specific quantities in its cosmic recipe. They are not numbers we invented. They are numbers we discovered. They appear to be woven into the fabric of space-time itself. They set the parameters for how everything in the cosmos interacts. They are the essential ingredients that make our reality what it is, from the smallest scale to the largest. Let's name a few of the main players. C. The speed of light in a vacuum. It is the ultimate speed limit in the universe. It connects space and time. It links mass and energy. E. mc squared. G. The gravitational constant. It sets the strength of gravity. Gravity clumps matter into planets. Gravity forms stars. H. Planck's constant. The master number of the quantum world. It defines the smallest chunk of energy. It governs the probabilistic rules that atoms must obey. It governs the probabilistic rules that particles must obey. These three numbers, C, G, and H, form the backbone of modern physics. They are not just abstract figures in a textbook. They have real, tangible effects on everything around you. The speed of light determines how fast information can travel. It sets the scale for communication. It sets limits on causality. The strength of gravity determines your weight. It controls the orbit of the moon around Earth. It keeps you from floating off into space. Planck's constant is why atoms in your body are stable and do not collapse. It allows chemical bonds to form. It enables the complex molecules that make up living organisms. These are not optional settings. They are the fixed rules of the game we are all playing. Because they are so important, scientists have poured immense effort into measuring them as accurately as possible. It is a painstaking process. Researchers use atomic clocks to measure time precisely. They use laser interferometers to detect tiny shifts. They use particle accelerators to probe fundamental interactions. They conduct experiments in labs around the world and compare results. The goal: reduce the uncertainty to the smallest possible fraction. This global, multi-generational effort gave us the numbers we use today. We trust these numbers to build technology and explore the cosmos. Our entire scientific worldview is balanced on the precision of these measurements. How do you measure something you cannot see or hold? How do you find the value of a rule that governs the entire universe? It takes incredible ingenuity. Measuring the fundamental constants is one of the great epics of scientific endeavor. It is not as simple as using a ruler or a stopwatch. These are deeply embedded properties of nature, and teasing them out requires clever experiments that isolate their effects. For example, to measure the speed of light, scientists have bounced lasers off mirrors placed on the moon and timed their return journey with atomic clocks of unbelievable accuracy. It is a cosmic scale experiment to nail down a single number. The gravitational constant, G, is famously difficult to measure. Gravity is incredibly weak compared to other forces. To measure its strength, you need to detect the minuscule gravitational pull between two objects right there in the laboratory. The classic experiment, first performed by Henry Cavendish, involves using a delicate torsion balance, a rod with two masses suspended by a thin fiber. When another large mass is brought nearby, the tiny gravitational attraction causes the rod to twist ever so slightly. By measuring that tiny twist, you can calculate the value of G. Planck's constant, h, lives in the quantum realm. One cutting-edge method is called the Kibble balance. It balances electromagnetic force against gravitational force, relating current and voltage to h. This experiment requires a level of precision so high that even seismic vibrations from a truck driving down a distant road can throw off the results. The effort involved is monumental. This relentless pursuit of precision is not just about adding more decimal places to a number. It is about testing the very foundations of our theories. Every time an experiment is repeated with better accuracy, it is a new test of whether our understanding of the universe holds up. When different methods yield the same result, our confidence grows. But if they were to disagree, if two different, carefully conducted experiments gave two different answers, it would be a bombshell. It would suggest that either one experiment has a hidden flaw, or more excitingly, that there is new physics waiting to be discovered. Now, let us entertain the big what if. Imagine that one of these constants is not what we think it is. We are not talking about a simple blunder, like a scientist misreading a dial. We are talking about a deeper issue. What if a constant is not truly constant? What if it changes over cosmic time or varies from one place in the universe to another? Or what if our methods of measuring it, which are all based on our current theories, contain a fundamental, unrecognized flaw? This moves us into a potential paradigm shift. It suggests a crack in the very foundation of physics. This is not as crazy as it might sound. History is filled with scientific truths that were later overturned. For centuries, astronomers believed the Earth was the center of the universe. It took the careful observations of Copernicus and Galileo to show that belief was wrong. Later, physicists believed light traveled through the luminiferous ether, but the Michelson-Morley experiment failed to find it, paving the way for Einstein's radical new ideas about space-time. Science progresses by challenging its own certainties. So, what would a modern ether look like? It could be a subtle assumption we have made without realizing it. For example, we assume the laws of physics are the same everywhere and at all times. This is a core principle, but still an assumption. What if it is only mostly true? What if the strength of gravity was slightly different in the very early universe? Astronomers look for this by studying the light from distant quasars, which probe laws of physics billions of years ago. So far, the constants look stable, but the search continues. The implications would be revolutionary. A hidden error could mean our theories are incomplete. The Standard Model has about 24 constants that must be measured and plugged in by hand. It does not explain why those values are what they are. Many physicists dream of a deeper theory of everything that would derive these constants from first principles. If such a theory exists, it might show our measured values are just effective constants for our current cosmic era. It might predict that under extreme conditions, like inside a black hole or at the Big Bang, the rules change completely. Section 5. When light changes its mind. The C constant. Let's start with the most famous constant of all with C, the speed of light. Its value, approximately 300,000 kilometers per second, is more than just a speed limit. It is a conversion factor between mass and energy. It is the thread that stitches space-time together into a single fabric called space-time. Einstein's equation, E equals mc squared, is arguably the most famous equation in science. Notice the C in there, squared. That means even a tiny change in the value of C would have a huge impact on the amount of energy released in nuclear reactions. The sun, which shines by converting mass into energy, would behave very differently. If C were just a little bit smaller, nuclear fusion in the core of our sun would be less efficient. To maintain its balance against the inward crush of gravity, the sun would have to burn through its fuel much faster. Its lifespan would be shorter. Stars across the universe would live faster and die younger. Conversely, if C were larger, fusion would be more sluggish. Perhaps stars like our sun would not ignite at all. The universe would be a much darker, colder place filled with failed stars. The delicate balance that allows for long-lived stars, stable planetary systems, the eventual emergence of life depends critically on C having the value it does. The effects would not stop with the stars. Time itself is relative, and its flow is linked to C. According to Einstein's theory of special relativity, the faster you move, the slower your clock ticks relative to a stationary observer. This effect, known as time dilation, is a direct consequence of the constancy of the speed of light. If C were different, this relationship would change. The clocks on our GPS satellites, which must be constantly corrected for relativistic effects, would instantly become wrong. Our entire global navigation system would fail. The very concept of simultaneity, of two events happening at the same time in different places, would need to be reevaluated. Even more fundamentally, C defines the boundaries of causality. Since nothing can travel faster than light, an event happening here and now can only affect a certain region of space in the future, a region known as its future light cone. This ensures an orderly progression of cause and effect. If C were suddenly different, or if it were not the ultimate speed limit, this orderly structure could break down. Information could potentially travel backwards in time, leading to all sorts of logical paradoxes. The speed of light is not just a number, it is the traffic cop of the cosmos, ensuring that the timeline of the universe makes sense. Changing it would unleash chaos, you know. Section 6. When gravity gets weird, the G constant. Now let us turn to gravity. The gravitational constant, G, determines the strength of the universe's most familiar force. It is the number that dictates how strongly two masses pull on each other. Unlike C, G is a tiny number, which tells us that gravity is intrinsically a very weak force. But its reach is infinite, and over cosmic scales, it is the undisputed king. It pulls gas clouds together to form stars, it holds planets in their orbits, and it shepherds galaxies into massive clusters. If you were to tweak the value of G, the entire architectural plan of the cosmos would change dramatically. Imagine if G were slightly larger. Gravity would be stronger. Here on Earth, we would all be heavier. Our years shorter, with extreme climate changes. The sun itself would be squeezed more tightly by its own gravity. The pressure and temperature at its core would skyrocket, causing it to burn through its nuclear fuel at a furious pace. It would swell into a red giant and die much sooner. What if G were weaker? A universe with a smaller G would be a much more diffuse and lonely place. Gravity might be too feeble to pull the primordial clouds together to form the first stars. Even if stars did form, planets might not hold on to their atmospheres. A weaker gravitational pull would let gases escape into space, leaving barren, airless worlds. A change in G could also solve or create cosmic mysteries. Galaxies rotate faster than they should, leading to the idea of dark matter, an invisible gravitational glue. But what if there is no dark matter? Some theories propose gravity behaves differently on galactic scales. In essence, that G is not a true constant. If this were proven, it would be a monumental shift. The mystery of dark matter might vanish, but it would be replaced by the even deeper mystery of why gravity changes its own rules. Section 7. The quantum quake, the H constant. Let us shrink down to the world of the very small, the quantum realm. Here, the ruling number is h, Planck's constant. This constant is the fundamental unit of action in the universe. It dictates that energy, at the subatomic level, is not a smooth, continuous fluid. Instead, it comes in discrete little packets, or quanta. The size of these energy packets is determined by h. Planck's constant is the reason an atom has a stable structure, with electrons occupying specific energy levels, orbitals around the nucleus. It is the foundation of all of quantum mechanics and, by extension, all of chemistry. If Planck's constant h were different, the very nature of matter would change. Let's say h were larger. Quantum energy steps would be bigger, atoms larger, bonds weaker and less stable. The intricate chemistry of life, DNA and proteins, would fall apart. Conversely, if h were smaller, atoms would be smaller and more tightly bound. The world would be denser. But the quantum effects we rely on for modern technology would be different. The entire field of electronics would have to be reinvented. Quantum phenomena like tunneling would happen at different rates, altering processes from nuclear fusion in stars to the operation of certain microscopes. In the hot, dense, early universe, quantum fluctuations, scaled by h, were stretched to seed all structure. If h had been different, the initial pattern would change, leading to a completely different large-scale structure. Or none at all, you know. The fundamental constants are not just rules for the present, they are the authors of our cosmic history. If we discover that one of these numbers is wrong, we would have to become cosmic historians and rewrite the whole story. 13.8 billion years depends on expansion, densities, and gravity. A stronger G implies a younger universe, a weaker G an older one. Since distance is light travel time, a different C would make our distances, and ages, wrong. Big Bang nucleosynthesis and the cosmic microwave background encode early constants. A mismatch between CMB predictions and local measurements would be undeniable proof our cosmic story needs a new chapter. So, the unthinkable happens. A series of impeccable, repeatable experiments confirms it. One fundamental constant is different. The first reaction, an explosion of focused, collaborative work. This is what science is built for. Verification, scrutiny, reanalysis, replication, systematic errors hunted, temperature, voltage, statistics. The immune system of science does its work. Once confirmed, theorists leap. A wrong constant means a new idea. General relativity, the standard model. The new value would break them, modify or replace. Perhaps string theory, loop quantum gravity, or something entirely new. Practically, we recalibrate. GPS timing, medical imaging, nuclear engineering, microchips. If constants differ, engineering principles get revisited. Software and hardware updated across industries. Culturally, unsettling yet wondrous. A global conversation about reality and knowledge, a new generation inspired. Museums and classrooms teach the revolution. We have journeyed through a universe of possibilities. How a tiny change could unravel stars, reshape atoms, rewrite history. Could such a fundamental error be hiding in plain sight, waiting to redefine everything we know? What are your thoughts? Let us know in the comments below. If this cosmic conundrum piqued your curiosity, subscribe for more deep dives into the universe's most profound mysteries.